for coming today. My name is Ajay Nahata. I'm a faculty member in electrical and computer engineering. Since this is Runs with an Engineer, I don't usually do this, but I thought I'd say a little bit about my background and then how it relates to this somewhat odd title. So I got my degrees in electrical engineering, bachelor's, master's, and PhD. I worked in the industry for about 12.5 years before coming here for two large multinational companies in New Jersey, Honeywell and NEC. And then about 10 years ago, I came to the University of Utah, and I basically came because I decided that I really like working with students and I wanted to do more research. And much of the focus of what my interests lie in, what my group has been working on, has been taking the sort of stuff that I did when I was in the industry, which is optics and optoelectronics, and looking at it from a more fundamental point of view. If you want to do more applied research or more applied work in general, industry may be a better place. Once upon a time, you could do basic research in industry. That's a little less true today, at least in terms of optics and physical sciences. So the work that I'm going to talk about, so I have this somewhat odd title, Optical Transmission Through Small Holes, and its application to ultrafast optoelectronics. So the sort of, just to give you a background as to what it is that we do, what the long-term goal is, and then I'll tell you about some of the details. So my background is in ultrafast optics, nonlinear optics. The idea is that we build our own homemade femtosecond lasers. Increasingly, we buy commercial ones, but some we make. We use that radiation, the optical pulses, to generate very low frequency radiation. In fact, what we do is we take pulses that are in the red and we translate them all the way down to the baseband, which means that we generate radiation from about 100 gigahertz to about 10,000 gigahertz. And the long-term goal is relatively simple. If you look at where computing and communications is going over the last 30 years, and there's a clear trend. People want things that are going faster, people want things that are smaller, and can hold more memory. Can't do much about the last one. But the goal that we're working on is really trying to develop devices and device technologies that will allow people to come up with systems-level capabilities that will operate at hundreds to thousands of gigahertz. So that's the goal here. And so let me start by talking a little bit about something that seems a little unrelated at first, and then I'll try to tie it all back in about 5 or 6 minutes. So if you think about just a sheet of metal, and you put a small hole in it, what happens is some light goes through it. So some light will go through it. And the amount of light that goes through it is relatively small. This thing acts like a low-pass filter, which means that, a high-pass filter, which means that high frequencies will go through this. The wavelength is small, low frequencies don't. And so you see this 1 over lambda to the 4th dependence, and the transmission goes as the diameter of this hole over lambda to the 4th power or 6th power, depending on how you normalize it. This is an idea that was developed back in the 1920s, and it seems sort of, whatever, but it's had enormous implications in nanotechnology, and I'll just briefly mention that in a few minutes. So the same thing happens if you have an array of these holes. So if you take a metal sheet, you put lots of these holes in a periodic array. What happens is that you get light that goes through in all of them. The holes to first approximation don't interact with each other, so you basically just add the number of holes and multiply it by the amount of light that goes through it. And so this isn't a new topic. It's been around for 100 years, in fact almost exactly 100 years. Lord Rayleigh first looked at this problem back in 1913. There's some papers of his that go back to 1894 where he talks about this. And so it's a remarkably well understood thing. So from a research point of view, the obvious question would be, why do this? Not only is it a theoretical issue, it's a pretty standard, common everyday application. If you think about a standard microwave oven, and it has this grate inside it. You can look in, microwaves ideally don't come out. What they do is they take a metal sheet in the window, they put holes in them. The holes are small compared to the microwave wavelength. They are large compared to the optical wavelength, so microwave radiation doesn't come out for the most part. It does with this 1 over lambda to the 4th relationship, so some microwave radiation does come out. But it's much, much larger than the optical wavelength, so you can see it easily. So this is a very, very well-studied problem. So from the research point of view, sort of the obvious question to ask is, so what? Okay, I mean, people know about this. They've known about it for 100 years, at least in theory. In applications, it's in every microwave oven. It's all over the place. Why does anyone here care? And I would say the same thing. In fact, 10 years ago, I did say the same thing. It's nice, but so what? And so what I'm going to talk about is some of the work that we've been doing. This started probably about 15 years ago when I was at NEC. One of my colleagues, Thomas Evison, showed that if you take a very thin piece of metal and you put these holes in, and they have to be at least at optical frequencies in gold or silver, and you put them in this periodic pattern, you don't get this 1 over lambda to the 4th relationship, you get this modulated transmission. And it was an interesting thing from a scientific point of view. People didn't understand it. They assumed that they understood everything about this, and it turns out that they were completely wrong. This is a very, the idea, and this is more detailed, maybe more than you want to know, but the idea is that it relates to what I referred to as surface plasmons, or surface waves. So there's been a lot of interest in this in general over the last 5 to 10 years. And so let me explain, without any slides, at least in the next minute or two, exactly why people care about this. If you take a standard optical microscope, and you look through a microscope, the smallest thing that you can resolve, the tightest that you can focus an optical beam, is on the order of about half a wavelength. So if you use, say, green light is at about 500 to 600 nanometers. You can see something in ideal cases about half that, so maybe about 300 nanometers, and that's about it. So with the push towards nanotechnology, with the push towards making things smaller and smaller, there's a problem. The problem is, how do you see things that you're making that are much smaller? And people can make things that are 10, 20, 30, 50 nanometers, but you can't see them. And so people have been trying to come up with ways of dealing with that. Sort of an associated application is the standard thing that I guess may not be quite as common anymore, but CDs and DVDs. So the way that CDs and DVDs work is you take a red light, you focus it down onto the CD or the DVD to the smallest spot size you can. You basically melt the polymer that's there, and if you melt it, it has this little divot, and that divot corresponds to a 1. And if you don't melt it and there's no divot, that corresponds to a 0. And so you create these over the entire surface of your CD or your DVD, and that corresponds to how much memory you have. Well, the maximum memory you can have is determined by the smallest spot size, which in turn is determined by the wavelength of your light source, which is 800 nanometers. So if you want higher density memory, what do? Well, you go to something like Blu-ray. What they've done in Blu-ray, they've gone from lasers at 800 nanometers to lasers at about 400 nanometers. Now the spot size is smaller by a factor of 2, the area is smaller by a factor of 4, the density, or the amount of memory, goes up by a factor of 4. You can't keep going that way because it won't work. You can't go into the UV and into the X-ray, there are no materials, and so they've now gone to these back-sided, double-sided DVDs and multi-layered DVDs. That only gets you so far. It's sort of the equivalent of multi-core processors. You can't make them faster, so you start creating many of them. So the idea here behind plasmonics is really different. You cannot focus using conventional microscopes and conventional optics to anything smaller than about half a wavelength. This idea of plasmonics, which is basically just light that's trapped just at the interface between the metal and dielectric. The dielectric in this case is air, so a metal-air interface. It turns out that under certain circumstances, if you structure that surface just right, you can focus down to something much, much smaller. In principle, 1/100th of a wavelength, 1,000th of a wavelength, or even smaller. In practice, there's some issues, but that's really the goal of what people want to do, and that's why there's so much interest in plasmonics. Our interest is a little bit different, and I'll say a little bit more about that in just a minute. I should just point out that I told you about this demonstration dealing with this array of holes where you get high transmission. This is a sample structure that we made years ago. It has a single hole at the center. It has these grooves around it. And the grooves don't go all the way through the metal, but they're cylindrical grooves. And if you look at the transmission, if you just take that bare hole, this is the transmission you get through the bare hole. If you take the bare hole and these grooves that go around it, at certain wavelengths that correspond to the periodicity between those grooves, you get about 100 times more light. That's fine. Why would anyone care about that? So this was done when I was at NEC, and the reason they cared about it is that they make laser diodes for memory. If you can get 100 times more light through it, means that you can use a laser that has 100 times less power. You can wrap this around something that's very small, so there's one of the things that people want to do is they want to make very, very small holes in, say, something that can move close to a sample, and if that hole is small enough, that determines the spot size that you can resolve. So you can, in principle, get down to 50 nanometers or 100 nanometers. So that's why there's a lot of interest in this. Our interest here at the University of Utah, once I left NEC, has changed dramatically. And so to try to explain what it is that we do and where it lies within the realm of optics and electronics, just the entire electromagnetic spectrum, or a reasonably large fraction of it. All the way down from low frequencies up to very, very high frequencies, the X-rays out here. So if you think about the low frequency range, meaning DC, or 60 hertz, this stuff here, all the way up to, I don't know, a few gigahertz. There are very well-developed techniques now for dealing with electronics, RF techniques in the megahertz, microwave techniques in the low gigahertz. So it's all extremely well developed. So people know exactly how to do this. And I should just make a point that people don't always fully appreciate. Whether it's 60 hertz coming out of the wall or it's a laser diode, they're both optics. There's really no difference. It's an electromagnetic field. And since it's an electromagnetic field, the basic ideas of what governs how it works is exactly the same. There is no difference whatsoever. So on the high frequency side up here, there are well-developed optical techniques. People have made lasers, they use a lot of nonlinear optical techniques to create all sorts of wavelengths. You can get from the green to the blue to the X-ray to the deep X-ray, you can do pretty much everything you want. There is this region in between that's referred to as the terahertz spectral region. It goes from about 100 gigahertz to about 10 terahertz, or 10,000 gigahertz. Traditionally, it's been called the gap in the electromagnetic spectrum, and it's called the gap in the electromagnetic spectrum simply because people didn't know how to make sources and detectors to get there. So up until about 30 years ago, when it says incoherent sources, what that meant is if you have one of those old-style ovens with the coil that you turn on and then it starts glowing red, that was a source for terahertz. A light bulb is a source for terahertz, but it's not a very good one. In fact, it's remarkably inefficient. And to detect it, you have to have liquid helium-cooled bolometers, which works great if you have a physics lab, not very useful otherwise. So over the last 20 years, people have developed techniques that are laser-like, meaning that you have to use lasers, but you can generate and detect terahertz radiation at room temperature. And the reason for doing this, as I said before, is what people want to do is they want to develop devices that operate at not 1 gigahertz or 2 gigahertz or 5 gigahertz, but 100 gigahertz, 200 gigahertz, 500 gigahertz, 5 terahertz. And so how do you do that? 10, 20, 30 years down the road, as people continue to want things that operate at higher speeds, when you want systems applications such as wireless communications that happens at high frequencies, how will you do that? You have to start well in advance. And about 30 years in advance is probably about right. Okay, so our goal is to, I'll restrict the talk to just one specific thing that we've been working on, that is optical devices. So if you look at electronics, and you look at the roadmap for what's happening in electronics over the past 50 years, you can go to Bell Labs, which is in Murray Hill, New Jersey. It's still there. And in the lobby, to the right of the lobby of Bell Labs, they have the Bell Labs Museum. And what you will see there is a lot of things, but one of them is the original transistor that was made by Shockley, Brattain, and Bardeen. It's a pretty ugly looking thing. It looks like 3 physicists soldered it together. It's this 3-dimensional thing, and it's actually pretty large. And then next to it, they have this bin that's probably about 3 feet wide and goes from here to the ceiling. And this was a demo that, I mean, this was something that they put up 30 years ago. And what they showed was that if you made a single transistor then, and you look at a microprocessor 20 years ago, that entire bin needed that many discrete components. There's been that much miniaturization. And since in the last 20 years, the amount of miniaturization has increased significantly. So people can now put billions of transistors and all sorts of other things onto a single chip. You look at optics, and where's optics? Well, the reality is optics is where electronics was about 50 years ago. One of the things that you want to be able to do in optical communications is you want to be able to sit and talk on the phone or type something on your computer, have that data sent to someone else. And that's exactly what happens today. It's done by fiber optics. But the problem is, fine, you're in your office, you call someone. How do you make sure that from the point of view of an optical fiber that goes from here to LA or here to China, that your signal gets put onto that optical fiber as an optical signal, not an electronic signal, gets routed to the right place and then split back up. And photons act very, very differently from electrons, so it's a much, much more challenging problem. So this is a standard device that we worked on probably about 15 to 18 years ago. It's called the reconfigurable add-drop device. So the idea was that you could heat it up and you could actually change which channels would get added and which would get dropped. It's a pretty rudimentary device. But the point of showing this is that 20 years ago, 15 years ago, this took an entire silicon wafer. One device took an entire silicon wafer. And there's a problem with this, aside from the fact that it's so large. The question is, why is it so large? Why does it not work? And so there's one fundamental issue. Actually, there are lots of fundamental issues. But there's a big one that people take for granted and don't think about very much. So if you look at what the real advance in miniaturization is, in electronics, you can do something relatively simple that you cannot do in optics. You can take a wire that goes from a device here, you can go up, you can turn the device to the right, and then have the electrical signal go to the device to the right. And that allows you to place them very close together. So you can have a wire that goes up like this, another wire that goes like that. You can make any sort of turns or wiggles or whatever you want. You can't do that in optics. And the fundamental reason is this. Think of driving a car. You're driving down the road, you're going at 10 miles an hour. You have to make a right turn. So it's fine. You're going 10 miles an hour. You don't have to even slow down. You can make that right turn. Speed up. Go 20 miles an hour. Go 50 miles an hour. Go 100 miles an hour. Can you make that right turn as easily? And the answer is, of course, you can't. There's no way you can do it. The same problem happens in optics. It's a higher frequency. Standard electronics works at megahertz frequencies, so it can make the right turn very easily. Optics works at 10 to 15 hertz. It cannot make that right turn easily. And so what will happen is, if you make a sharp right turn, the light will just keep going straight. And so you have to make these very, very shallow turns. And these very shallow turns require that you make a very large device. And even though people have been working on this for 30 years in optics, they still have absolutely no idea how to solve this problem. So about 10 years ago, people came up with this idea of what's referred to as a photonic bandgap structure. The idea is you take a silicon wafer, and this is a variation of some other work that's been done, and you put holes in it. And if you put holes in it in just the right geometry, you can make it so that it acts like an equivalent of what happens in a real crystal. And in principle, light could make it around the bend. And in fact, there were simulations that showed that this would work beautifully. And it does work beautifully. Light makes a 90-degree bend. The only problem is that you get 20 dB loss per bend. That's the trade-off. So it makes the bend, but nothing goes through. And so it's not very useful. The second you have two, actually even after one, there's nothing left. So it is one of the fundamental problems. And like I said, no one's come up with a solution yet that really works. There's a second problem. And the second problem is that, if you think about a silicon wafer has some natural SiO2, silicon dioxide on top that just naturally grows. You put some wiring on it. Whether it's in this form or in the form that's in the microprocessor, it doesn't actually matter very much. What will happen, even if it's a straight line, what's going to happen is you've got this electrical pulse that is between these two wires, same as what happens in this outlet here, and it's propagating along. Part of the electric field is above the silicon wafer, part of the electric field is inside the silicon wafer. Well, signals travel at the speed of light. These signals will travel at the speed of light, but at the speed of light within that medium. So up here in the air part, it'll travel at the speed of light. In the silicon, it'll travel at the speed of light divided by 3. 3 is the refractive index of silicon. And so it propagates 3 times faster in air than it does in the silicon. So what's going to happen to your pulse is going to start moving apart. The part of it in the silicon is actually going much slower than the parts in the air. And because they propagate at different speeds, what will end up happening is it creates a shock wave that sends most of the radiation into space. And so that radiative loss goes as the cube of the frequency. Once you get above about 500 gigahertz, it becomes very bad. In fact, you can't really go more than about a millimeter at frequencies above 500 gigahertz. And so this is a separate problem that has nothing to do with bends and all the other stuff. So we've been working on this first problem and a number of other issues. And I'd like to spend, well, I've probably spent more than my time, but I'll spend a few more minutes until food comes just to talk about what we're doing. So we're trying to make things that are equivalent of those wires but have very low loss. The idea is we make holes. So this is where the holes that I talked about at the very beginning of the talk come back in. They're now not circular holes. In this case, we make rectangular holes. The shape matters, the length, the width, the periodicity that you have here. So all of these parameters, S, A, D, all of those matter. This is what it actually looks like in a piece of stainless steel. When you launch, in this case, we generate terahertz and we launch it on this thing. It actually propagates along this thing, but only set frequencies. Which frequencies? Well, it's determined by the parameters of these holes. So only certain frequencies, not all of them. We can actually go and test it, and I won't go through the details of this, but we basically use an ultrafast optics approach. We take the femtosecond laser that we have, we generate terahertz radiation, we couple it to this waveguide, and this waveguide is made of metal and air in the holes, but it's no different than an optical fiber, it's just a different shape. And we can test exactly what propagates along and how much. We can look at what happens in terms of focusing. You can use these things to make lenses, to do all sorts of stuff, but now a wave that's bound to the metal interface. And we can actually look at all the propagation properties. So we can see what the loss is as you propagate along this thing. Turns out that it can propagate about 12 to 15 centimeters rather than 1 millimeter. And so it works much, much better, obviously. It has a Gaussian profile, and all that means is it has a Gaussian profile that surrounds this hole. So it's really bound to that. The fact that you make these holes means that the wave is now attached to that structure. And it follows it, even if it turns. So you can make these Y splitters. You can have light come in at the top, terahertz, and it splits into these two arms, and you get a 50-50 beam splitter. You can make a 3dB coupler, and so that's a picture of a 3dB coupler, and this is its size. Now, the size is important because, as I said, what people want is they want things that are smaller and faster. The faster we can deal with, the smaller we'll have to work on. This is large. There are other approaches, and the other approaches that people use, just so you know, is they're working on the other direction. They're making things much, much smaller and worrying about faster later. So they're working on things made out of doped DNA, carbon nanotubes, things that are inherently on the order of 100 nanometers, but they don't know if they can go much faster. So we're trying to address the same problem, but from different ways. And so recently we've been working on trying to come up with new ways of designing these things, new ways of doing fabrication. How do you create these sorts of things? So we've made these 3D structures so the waveguides can actually go and change planes. And this uses a commercial 3D printer. There's nothing very fancy about it. You have to have a good printer, obviously. But you can make one out of a polymer resin, coat the thing with metal, and it works well. You can show that it works well as a 3dB splitter, so you get 50-50 splitting. You can make far more complex geometries. So this is only one specific direction that we're going in, but what we're really trying to look at is how do you make the broad range of device capabilities that are necessary for a systems level application? How do you make waveguides? How do you make filters? How do you make modulators? How do you make switches? How do you do all of these things, not only as passive devices, but also active devices? Things that can be tuned, things that can be reconfigured, things that can switch in principle very quickly. And ultimately, what you have to have are you have to have things that not only carry terahertz, that's the carrier frequency, but will allow you to switch those frequencies at very high rates, 50 gigahertz, 100 gigahertz. That'll take a little bit of time. So with that, let me just conclude. Hopefully I've shown you that we're doing some things that I think have some potential. It's research, so God only knows. But there are real needs that people have and will continue to have in the coming decades. And so people have to start looking at those now. So one final point that I do want to make, and it's why I said a little bit about myself at the beginning. So I think for all of you, and this is a Lunch with an Engineer program, so the issue that you have to think about in terms of your own future, I've gone a very circuitous route. I did my undergrad, did my master's, decided to leave for 5.5 years, go and work in industry, went back for a PhD, went back to industry for another 7 years, then came to academia. It took me a while to figure out what I really wanted to do and what I love, and this, I found it. Took a little while, but I found it. So the thing for all of you to think about is, what is it that really motivates you? What is it that you want to do with your life? It may be in academia, it may be in industry, it may be doing something else. But you really need to start thinking about it now. Find something you have a passion for, and don't worry too much about whether or not it is the latest thing that people are working on. I mean, as I said, we started working on something that people thought they understood 100 years ago. There are always lots of interesting things to do in the world. There are lots of ways to rethink things that people thought were settled issues long ago. And so I wouldn't be overly concerned about that. Find something that you want to do with your life. With that, thank you very much. So if anyone has any questions about this or anything else, I'd be happy to answer them. Yeah?
So, is there a way to make like a or nanoscopic mirror that could help you change the rest of the light?
Yeah, so people are working on that. I mean, we're not trying to do that, but people are making, this is more in the area of dynamics, people are making mirrors, for example, where you can fabricate them on a wafer and you can individually address each individual mirror separately. And the value in that is for image processing, but also for communication. So if you think about a communication